Hi, welcome to the second stream, and very, very excited about this one as well, because it is actually quite a big paper that we're going to tackle today. Still working on the background music, so do apologise, but obviously the content is really, really important as well. So in today's session, what I'm going to be doing is I'm going to be working on the Tuesday, 2nd June 2015 afternoon ASGCE chemistry paper from F322. So it was change energies and resources. The big paper, really, it was 1 hour 45 minutes. Let's get straight to it. Let's see what the questions are all about. You can have a look just below. See all the different topics that came up, but bear in mind that there are quite a few tricky calculations on this one. It's the general comments that the examiners were able to give, having reviewed all of the questions, but that there were a good range of questions that provided candidates of all abilities the opportunity to demonstrate knowledge and understanding of a wide range of chemistry. So recall and explanations were in questions 1, question 3, question 5 and question 6, and there's a lot of evidence to suggest that the examiners actually had prepared well for the exam. The ones that had more demand in terms of drawing diagrams accurately included question 5A, question 60. We've got the written explanations in 4, 5 and 6 as well, and the applications and analysis, which is 6 and 7 and 7. So you can generally get an idea that at the end of towards the end of the paper, it was a lot more demanding than the start of the paper as well. But let's have a look at question number 1. Starts off with a nice simple alkanes question. Most are able to describe structural isomers. The answers you can see as well at the bottom of the page, so just have a look. Pause by all means if you want to pause, and just see if I can actually blow it up a little bit just to help you. No problem at all. So we've got compounds or molecules having the same molecular formula but different structural formula. A straightforward answer there for a simple 1 marker. You've got a little more difficulty with the name of the compound A. So what you've got to realise is that it's common to come up with maybe incorrect answers. Sometimes people misplace the locant numbers, that's the 2s and the 3s. So some people suggested, for example, 2,3,3-trimethyl butane. Sometimes you find that you find that answers could be with inappropriate nomenclature as well, so 2,2-dimethyl. 3-methyl butane is something that I've seen happen as well when candidates tackle it. Small proportion, actually, believe it or not, name this as heptane. You've got 1, 2, 3, 4, 5, 6, 7 carbons there. You can actually realise why. I mean, I'm not entirely sure what they covered when they covered organic chemistry there, and then if they're actually talking about that as being heptane. So there you go. So get that right. It is 2,2,3-trimethyl butane. They do allow trimethyl butane as the only alternative response there. Okay, right, let's move on. So a molecule of an alkane has 24 carbon atoms. The empirical formula has to be C12H25 because you can simplify the 24 down to 12. You've also got 24. Use the N plus 2 for the hydrogen. 24 times 2 is 48 plus 2 is 50. Simplify it, and you've basically got your C12H5. That's an easy one. Okay, multiples allowed in the next one. It's a construct for the equation for the complete combustion of octane. Generally, what I would recommend is that you have a look at the number of carbons first. The C8, it is complete combustion, so you've got to have 8 molecules of carbon dioxide, and then you can just simplify it with 18 goes down to 9, so you'll have 9 molecules of water, and that's half the credit already. All you'll then need to do is count up the oxygens, divide it by 2. You can put 12.5 oxygens, absolutely fine. You can, if you don't really want to do that, you can just double everything up to, you can have 25 oxygens. Ignore state symbols. You don't have to worry about state symbols when it's a simple 1 marker. Okay, now the next question is a little bit tricky. You've got show the combustion was complete, so you have to try and figure out how much would actually be produced if it was complete combustion. So 36.48 grams, maybe what would you have to do? Would you have to maybe work out the number of moles of octane that you had? Remember, it's C8H18. So you could work out the number of moles that you start off with. Number of moles equals mass, which is 36.48 divided by the molar mass, which is that 18, as I just mentioned. And then what you could do is you could think, right, okay, I've got my complete combustion of octane. How much of that octane would actually be, how much carbon dioxide rather would actually be made? So for every mole of octane that you start off with, you make 8 moles of carbon dioxide. Then you can use Avogadro's law to deduce, because you've got 1 mole of gas would actually make 24,000 centimeters cubed. The question could develop into that, but I would actually just keep it simple. Obviously, you don't need to go into that much depth with this one. It just says 2.5 moles of carbon dioxide. Show the combustion was incomplete. So let's have a look at the answer. From the complete combustion, you would actually have predicted that 2.56 would be produced. 2.50 was produced. So there you go. Simple as. Okay. Calculations there, just for references. So have a look at those. So out of 10, I would say maybe that one would probably be like a 4 out of 10 in terms of difficulty. But make sure you don't lose any marks for that. Okay, right, I'm going to move on. Part E. Not a party, obviously, Part E. Part E, now in actual fact, most candidates actually identified these 2 processes required as fractional distillation and cracking, so no problem at all. However, apparently it was not uncommon to see responses that included reference to other processes. So don't put in reforming, don't put isomerization or anything like that. Okay, it's just not going to get the marks at all. All right, okay. Equation for the preparation of ethene from an alkane. Again, you know, majority of candidates should be going into that exam knowing this one. It is something that is answered very well. Show the formation of ethene from an alkane. Let's just have a look at it. Correct equation. Make sure it's done. Okay. Okay, right. Let's move on to question 2, part A. Butan-2-ol can be prepared using 2 different methods. So you got, now this is actually this is a really, really interesting question as it develops. But first of all, let's talk about the atom economy of each method, giving you reasons. Right, so have a look at this one. You've got method 1, which produces 100% or only one product, which is absolutely fine. That's all of those atoms plus all of those atoms, making all of those atoms in the molecule. Okay, so that's nice 100%. Whereas over here you can see that the bromine has to disappear somewhere, so the atom economy is less than 100%. It's just a quick comment, 1 for one, 1 for the other, 2 marks. Very, very nice. Okay. 2 part B. 2 part B, acid catalysis is required. Obviously, you just need to protonate that. Where is it? Let's have a look. You need to, if you 2 part B. Sorry, just want to read the question again, make sure I'm getting it right. 2 part B. So method 1, what you want to do is you want to protonate the what do you call it? The water molecule, I believe. Just double checking this, and then what? Then what you will actually have is, oh, actually, let's hang on a second. Yeah, it is an acid catalysis. Do bear with me. Acid catalysis, mineral acid, do not allow weak acid. So what is actually happening over here? You've got the proton, you've got a carbocation forming. Got the nucleophile going in there. Yeah, definitely you would need an acid catalysis for that one. That's fine. Might come back to that one. Don't allow a weak acid. Ignore pressure. Ignore temperature there. Okay. So what does the examiners actually say on that one? See part 1. Sorry, part B. This question was answered well, and the majority of candidates identified a suitable catalysis. Now, why was nickel actually an incorrect response? Well, obviously, the answer for that is that nickel would break the double bond would not break the double bond. Nickel would actually break a hydrogen molecule up, and that would actually a nickel Rainey catalyst would be for the hydrogenation, adding hydrogen across the double bond with that one over there. But you actually need a proton there. Okay, right. So let's just move on from that one. Average bond enthalpies can be used to calculate enthalpy change. Now this is quite interesting because the new specification doesn't actually ask you to define it, it just asks you to be able to explain it. So it's a little subtle thing there. Let's see what the examiner said. Candidates were required to recall the definition of bond enthalpy in this question. A range of responses were seen. Most recognised bond breaking was important, but weaker responses including contradictions by also referring to bond formation. The strongest candidates were able to state that bond enthalpy referred to 1 mole of bonds. It was not uncommon to see answers such as 1 mole of compound and 1 mole of substance. Now the good news is that you don't actually have to do this for the new OCR. Okay, so you don't have to start referring to 1 mole of broken bonds. So we're going to move on very, very quickly on to enthalpy change of reaction. So the big thing about this question was that there are multiple answers that you could get for this one. The most common one is minus 970. And you would actually get this if you were. You could actually get this answer through several methods, right? It's method one. So you can actually get this by counting up all of the bonds in your products, counting up all of the bonds in your reactants, breaking them all up, and then just doing all of the addition. But there is actually a nice little shortcut that you can take. So let's say, for example, if you're thinking about the total differences, there's no point in thinking about breaking up bonds and then making bonds if the parts of those molecules are exactly the same. So why don't just ignore the CH3 there and the CH3 there, because you're going to have to dismantle that one and you're going to have to reform it. Total energy change is 0. Do exactly the same for this one. So that's the CH3s over there. Do exactly the same for the CHs over there. Do exactly the same thing over here. So the only thing that you're breaking then are the C-double-C bonds there. You're forming the CH bond there. You're forming a CC bond there, and you're forming a CO bond there, and you're forming a COH bond. Now, here's the big trick. You may have forgotten that you actually need to break up H and O in the process as well. So you could just ignore one of the OHs. You don't have to put that in the calculation there, and you must make sure that you incorporate breaking up that water molecule as well. If you don't, you'll get a value of around about 970. If you didn't bother about your definition of average bond enthalpies, then you actually get a different sign. If you do take all those things into account, you'll get the right answer with minus 42. Now there is a nice little hint that's given. If you have forgotten about bond enthalpies, the average bond enthalpies that are given are positive, so that means to say that the bond enthalpy is actually defined as the amount of energy that you need to break the bonds. Okay, so use that and you should be able to see yourself through with that question. Okay, so we're going to move on now to part D. Method 2, percentage yield method of butan-2-ol is 80%. Calculate the mass of 2-bromobutane. Give your answer to 3 significant figures. Obviously, don't miss that last bit out, otherwise you will drop a mark. Say 3 significant figures required in the answers. Your actual is there, and then your theoretical is there, and then it's and then work out what your actual is compared to your theoretical. The actual would be actual divided by theoretical multiplied by 100. That would be your percentage yield. So then refer that back to what the information is that they've given, which is 80. Rearrange that, and you should then be able to work out the number of moles that you actually got, and then work out your overall mass after that. Okay. Right. Okay. I'm going to move on. Oh, by the way, how did people do on that one? 2A Part D. In general, candidates cope well with that more demanding calculation based on percentage yield. Hello. Okay, bye. Most are able to calculate the number of moles of butane-2-ol, and a stronger scale is correctly to give the moles of 2-bromobutane required. But the common mistake was to scale by a factor of 0.8. I'll just show you the question again. A factor of 0.8. rather than 1.25. However, error carry forward marks were awarded. Majority of candidates scored 2 or 3 marks in this question. That sounds really, really good. Okay. Oh, by the way, did we say what the actual answer was for the last one? Just to confirm, it was minus 42 kilojoules per mole. Okay. Right. Okay. Quickly moving on now. So, methanol, CH3OH, is an important feedstock. Now, this is describing and explaining the effect of increasing the pressure on the reaction rate. So let's just have a look. You've got 4 volumes there, 4 molar volumes of gases there. You've got 1 molar volume too. So if you increase the pressure, it's going to try and squeeze back in, so it's going to move forward. That's what my initial response would be. The effect of pressure on reaction rate is well known by candidates at this level. Many scored 1 or 2 marks, and examiners were encouraged. A significant proportion of the cohort scored the first mark, relating the increased rate to the increased concentration of the molecules, rather than vaguer responses in terms of the relative proximity of the molecules. Weaker responses focused on the equilibrium rather than the explanation of how the rate is affected. Candidates are advised to take note of key terms in questions, especially those in bold. So remember that rate is in bold, as they often give guidance as to what is expected. So start talking about the rates. Okay, give your answers in terms of increase in rates, greater concentration of volumes, molecules. Obviously, you've got more in there. They are. It's not just, you're going to bring them nearer. What you want to do is you want to say, well, there's more collisions per second. Those collisions are more frequent, and therefore you're going to have a higher reaction rate. Okay, the Chateliers principle. All right, position of a dynamic equilibrium shifts to minimize the effect of any change. If you want to just shorten it to a 1 marker, the equilibrium shifts to minimize any change. Simple as that. Keep it there, okay? For a nice, simple 1 marker. See part 1. So, high pressures and low temperatures would give a maximum equilibrium yield of methanol. So you've got this. You've got to try and explain it in terms of the Chatelier. So let's just have a quick look back. So this is an exothermic reaction. And if it's an exothermic reaction, if you if you think that the forward reaction is exothermic, remember it's an equilibrium, but if they give you a value that's expressing what's happening in terms of the forward direction, the forward reaction is exothermic. It gives out heat. You could say that the reverse reaction is endothermic. So if you are actually, let's just refer back to the question over here, low temperatures. So if you are lowering the temperature, what you want to do, what will happen is that the system will respond in order to raise the temperature, and the equilibrium will actually be shifted to the right hand side. Similarly with pressure, if you increase the pressure, you've got the right hand side which has fewer molecules on it. So what's going to happen is, again, you're going to have a shift to the right. So make sure you've just got a proficiency on that. You should be fine for 3 marks, okay? So 1 mark will be given for stating what happens at the temperature, 1 mark will be for the pressure, and then knit those both together to start talking about the position of the equilibrium. Why do the actual conditions, why are the conditions different? Well, if you lower the temperature too much, you won't get enough for the activation energy, okay? Lower the temperature gives a slow rate, but also high pressure means to say that it's expensive, and as well as that, you've got greater risk because high pressure environments can be quite explosive if you haven't got your proper walls and things like that. So think about that. It's a safety risk. Don't start talking about high pressure, however, being explosive. It's a really, really kind of flippant thing. It's about safety risk. It's about how it could be, how it would need to be. What's the word I'm looking for? It would have to be enforced. Okay, your actual casing in your industry. So as a result of it, thicker walls, more safety would mean more expense. All right, okay, let's move on. Catalyst, you've got methanol with a catalyst. Boltzmann distribution, straight Boltzmann distribution. Make sure that that's there. The curve must start at the origin. So it starts over here, and see if it is traced. It starts at the origin, and you must not touch the x-axis at any higher energy. Okay, so it must tail off like this. Okay, and obviously it must peak. It's a very, very standard standard response there. Please make sure that you put the actual labels for the axes as well, number of molecules and energy. Okay. What does a catalyst do? It allows the reaction to take place at a lower temperature. Okay. If you are really stuck on words with that, just make sure that you say less heat. You will get the mark. Okay, quite a nice question that was. Okay, we're going to move on. Now, do bear in mind that the questions that you will get in the new GCSEs, gosh, I wish it was GCSEs, in the new A-levels are actually going to incorporate Carning-Gold prelogue, systematic naming, and so what you need to do is you need to be able to, when you're doing your past papers, do bear in mind that things like Markovnikovs are not necessarily something to be found. Talk to your teachers, try and get some good practice from the textbooks, but they are straightforward as well. Make sure you revise those points as well. But anyway, polymer PTFE, polytetrafluoro ethene. Obviously it is B, break that, join it up. So this is all about polymerization. Nice simple one marker there. Polymer H can be disposed of by combustion. Let's have a look. The structure of the monomer for H. Now obviously it's CH3Cl, CH3Cl, and HCH3, HCH3. So it's really this section over here that is the repeating unit. Just lop that one off, turn it into a double bond, hey presto, you've got it. Okay. Acidic toxic gas that could form during combustion of H, I would guess, is HCl. There you go, easy HCl. Let's move on. G suitable for an aerosol. So let's just have a quick reminder of what G looks like. Let's have a look. Okay, well, you can imagine that this would be tetrahedral in shape, and how would it be binding? It would be a simple covalent molecule, so you'd actually find that there are low intermolecular forces between those molecules. That means it would be volatile, it would have a low boiling point, not very reactive, because all of those halogens, you've got fluorine, that CF bond is extremely strong, that CCl bond very, very stable, so it wouldn't really react with very much. Low reactivity, volatile is absolutely fine, low boiling point instead of volatility, non-poisonous, non-toxic, okay. Those are suitable properties, state two sensible ones, okay. I tend to think about when I'm doing these questions, I tend to think about Teflon layers on, which is PTFE. I would think about Teflon layers and their use in frying pans. Obviously, we couldn't use halogenated polymers, halogenated compounds if they were not inert, if they were harmful. So just think about it like that. All right, okay. Right, we've got an ozone layer question now. Explain the following statements using equations. So, life on Earth benefits from the presence of an ozone layer. Concentration of ozone is maintained in the ozone layer, and you've also got compound G that produces radicals, which catalyse the breakdown of ozone. So, in terms of benefit of ozone layer to life, that would be something to think about. Ozone absorbs that UV radiation, and the UV radiation that reaches the Earth's surface then as a result is reduced. Okay, it's a nice easy mark for you to pick up. And you've got the concentration of ozone is maintained in the ozone layer. So in actual fact, you've actually got O3. There's a little glitch in the mark scheme over here, but it should be O3 in an equilibrium with O2 plus O with a radical. So that's actually something that is maintained, because that O radical will then start to react with O2 again, and it will stay there. Now the production of radicals from G catalyze the breakdown of ozone. So you actually find that the actual halogens, the halogen, what should we call it? The CF. The carbon halogen bonds, they can actually be weakened and broken, especially with that UV. That actually forms radicals, and then those radicals then start to attack the ozone as well. So try and put those equations down, and you should be able to secure a lot of good marks on that bit. There's a lot of space given for that, so do be careful. I'm going to see whether I can zoom into zoom into the answers for that, because we want to try and make sure that we get these equations right. Here we go. So you can get a quick easy mark with the benefits, and then you've got, that should be an O3, so write it as O there. O3 reacts to form O2 plus O, that's the radical. Then you've got, that should actually say CF2 Cl2 reacts to form Cl plus CF2 Cl. Okay, that's your production of radicals, your initiation, so to speak. And then you've got the breakdown of radicals. Cl radical plus ozone reacts to form ClO, and that's that is attacking the ozone. That then forms ClO plus O2, and that would be a radical in itself. Or you've got ClO plus O radical reacts to form Cl plus O2, or you've got ClO plus O3 reacts to form Cl radical plus O2. You notice that those propagation reactions are taking place, always producing a radical that can then just further react with ozone. Okay, all right. Okay, let's move on. Alternative ozone-friendly compounds are used as propellants now instead of the compound G. Which of those compounds would be suitable for it? And the answer would be D. Let's just remind ourselves where D is. Excuse the scrolling. Just goes to show, you've got to make sure that both pages are open. Okay, so D would be a better suitable alternative. Okay, it's obviously low volatility, and it's got a H in there as well. Okay, I'm assuming that it would be a better one because it's got only the one CCl bond instead of two. Okay, right. Compound C and F can be analysed to obtain infrared and mass spectra. Okay, so by this stage you must be feeling very, very tired. You've had lots and lots of wordy ones, questions. And now we've got some analysis that we have to start to think about. What happens to molecules when infrared radiation is absorbed? Bond vibration. Now, I did promise my A-level students that I would be doing the following actions. So the bond, it can actually vibrate like this, or the bond can bend like this, or bend like this, or you could have stretching of the bond as well. Okay, but you must make sure that you actually have the word bond there. Suggest that the molecular formula of two ions are responsible for the peaks in the mass spectrum and that in the mass spectrum of C that are not in the mass spectrum of F. Do we actually have it? So what would be present? You've got ClC. Okay, all right. So you would actually have. I'll just quickly refer to it. Oh, I've skipped too far. Sorry. Okay, so you've got a Cl3. So if this was actually broken through mass spectra, you actually could cleave that, and you would actually find that you have CCl3 plus present there. So that would be that bit. That would not be present in that one, in F. And then you've got the presence of this fragment ion, which would not be present in that one because there's only one fluorine. Okay, skipping on, back page, thank you. Right, okay, an allyl bromide is used in the production of polymers. All right, so we're going to move on now to structures. All right, the really powerful diagram, this p orbital diagram, make sure that you do know it. So the first mark is given for the label diagram with the p orbital, and then the second diagram is given the label on the right showing the pi bond. So make sure you learn those diagrams, okay? Keep sketching them until your exam. Homologous series, same functional group, success with each successive or subsequent, and that's in bold, each successive or subsequent member differing by CH2. General formula, it would be CnH2n minus 1 Br. So just have a quick look at that. Where is the question again? Okay, so if you had another additional one, you would actually have, let's have a look. The answer is CnH2n minus 1. So that's a C, that's a H, CH2, so you'd actually have an extra CH2 That, yeah, that works out. CnH2n-1Br would be the next one up. Just double checking, which has allyl bromide as the next homologous series. Let's have a look. So you would have CH2, CH2. Yeah, it does work out. It does work out. Okay. So next question: 3-bromo prop 1-ene. You don't have to put the the 1 in brackets. Prop-ene is absolutely fine. Have I gone too far? Sorry about this. See, I have gone extremely far. Here we go. General formula. Right. Okay. Give the systematic name. Yeah, systematic name for allyl bromide. That would be 3-bromo propene. Let's move on. Reaction mechanisms. Curly arrow. It's the movement of an electron pair. No problem at all. Nucleophile, except a nucleophile is something that hunts the nucleus. You can think of it like that. Nucleophile, and it's got an electron pair, and it donates it to that. Okay, so can donate a species that can donate a lone pair. It's common answer. Right. Okay, let's have a look at the mechanism. See whether that that gives us anything to be concerned about. Let's have a look. Right. Okay. So I hope you can see this. Let's have a look. So the mechanism, you can see that that's the nucleophile. Curly arrow straight from the lone pair directly into the actual centre. Do you want to take a seat here? You can, Phil. Sorry. Here we go. Curly arrow straight from the OH. Notice that the lone pair is going straight into the carbon atom of the CBr bond. You've got delta positive because that is obviously more electronegative than that, and very straightforward mechanism there. Okay, make sure that you've got all the dipoles. This is a nucleophilic substitution because the Br comes out and it's replaced. You've got allyl bromide reacts with bromine, so you've got addition across the double bond here. So again, make sure those pencils are sharpened, and it's side on as well. Okay, so it's, so that one goes straight into the Br delta positive, and then what you have in the next stage is you have the Br anion nucleophile then adding across back into the carbocation. Okay. Right. Okay. This is and the carbocation is that one. So use Markovnikov's rules in order to predict correctly what the product will be, and it is an electrophilic addition because the original Br2 is attracted to the double bond, which is electron rich. So and the Br2 adds across the double bond. Right. Moving on. Reagents and conditions for step 1. Here you can actually say it's hydrogen and nickel catalyst, and with step 2, it's you've got a mixture of organic products. Whenever you have a mishmash of different reactions taking place, and you've got Cl2, you've got to instinctively think UV. It is going to be some kind of radical reaction. Okay, and that's what's being outlined in step 2. I really like part 2 of this question because this is like your standard initiation, propagation and termination question. So just pause it if you need to. Make sure that you know all of the different steps. Just follow that through. Just scroll up to termination. Okay, so what you've got to do is you've got to assign initiation, propagation, and termination to one of each of the reactions. Okay, right. We're going to move on. Basically, the mixture comes about because you can form the radical the bond that actually breaks could be any one of those, and then the bond and then the center that it attacks. It could be anything in that molecule, so it's very indiscriminate. Whichever one that falls apart, it's very indiscriminate. Whichever bond together, and also you'll get more complicated further substitutions taking place as well. Okay, so just summarize that, you'll be fine. Okay, right. Enthalpy of combustion. So first thing that you need to do is calculate the amount in moles, and then calculate the enthalpy change of combustion. Give your answer to 3 significant figures. That's your moles. Okay. So 1.54. Okay. Of alcohol J. Number of moles. We already have the molecular formula as well, so you can work out the molar mass. Number of moles equals mass over molar mass, and then the enthalpy change. Scale it back to scale it back to 1 mole, and then scale the enthalpy changes down to 1 mole as well. And that's basically what's happening over here. You got your energy. Q equals mc delta theta, E equals mc change in temperature from GCSE. So this is actually covered in the triple science now, so try and think back, and don't forget to round up or round down. You've got 3 significant figures. Okay. Why do you not get that? In reality, you've got heat losses, but you can't use that one. Incomplete combustion, that's a nice subtle one. You've got non-standard conditions, you've got evaporation of the alcohol. Think about the alcohol evaporating before it's actually burnt. Think about the water, it might evaporate while it's being heated. You've got specific heat capacity. We're assuming that all of the energy is actually passing straight directly to the to the water, so think about that. Right, okay. Standard enthalpy change of formation. 5C plus 6H2 plus half O2 reacts to form C5H12O. So next question. Enthalpy change of combustion from the information given above. So you've got your combustion products at the bottom. Let's just have that. No, these are your combustion products. You've got C5, so you've got 5C forming, you've got 6H, that's why it's given previously. You've got 7.5 O2, so that joins up with an O to make 8 O2, so you have 8 O2 over here, and then so you've got your constituent elements. So this would be a Hess's law one. So think about how let me just check the complete combustion. Calculate the enthalpy change of combustion of alcohol J from the information enthalpy change of combustion. So you know what the enthalpy of formation is. So that would be minus 366 that way. So this way it would be plus 366. You've got no enthalpy change of formation between element and element, so you can ignore the oxygen. The enthalpy change of formation of 5CO2 would be 5 times minus 394. This one is minus 286 times 6. So in total, you've got plus 366 plus 5 times minus 394 plus 6 times minus 286, and that should give you your answer. You should work it out to be, minus 3322. Minus 3320 kilojoules per mole. Okay. Right. You've got an infrared, no broadening. Okay, so you've got a very sharp peak. Determine the structures. Let's see what the clues are. Oops. So let's see what the clues are. Determine the structure. Now, you've got evidence of the IR absorption at 1720. That is a clear indication of the presence of COO, the carbonyl group. You've got no carboxylic acid absorption, no peak between 2,500 or 3,300, and you also then need to infer that it is a secondary alcohol, or K is a ketone. Okay, so that is a secondary alcohol. Remember, you don't get when you oxidize a secondary alcohol, you do not get carboxylic acid. It just stops at a ketone. That's pretty much what's being implied here. So it's only easy when you know what the answers are, but Make sure you give a balanced equation as well. Just use square brackets O for representing the oxidation state. Now, what might be interesting is that they might actually combine that with something a little more advanced because it's a terminal exam, so just be aware of that. But at AS, you can just represent it as a square bracket. So the alcohol J is soluble in water. The reason why it's soluble in water would be to do with hydrogen bonds, and pop that diagram out. I'll just blow this up just to show you what it should look like. So you've got your hydrogen bond there. It's a rated hydrogen bond. Delta plus, delta minus, delta minus. One common question that I get asked about is are the lines. If the diagram's not labelled, allow hydrogen bonds or H bonds from the text. So just make sure that you put it in your explanation as well as the diagram. It is only a 1 marker, so don't fret about it too much. Another blank page. We love blank pages. Okay, right. So final question is an analysis. So the flowcharts show reactions involving these compounds. And you've got your different percentage masses. Now there's something, a big giveaway, broad spectrum there. The empirical molecular formula for compound L. Let's just see what the answers say. Oops, scrolling through. Okay, so the empirical formula, all you need to do is work out what the molar ratios are. So divide by 12, you've got divide by 1, divide by 16. So you should have 3.3, 6.67, 3.33. Make sure you don't lop off any of the figures. The empirical formula is CH2O, and then the molecular formula is something you just times it by 3. That's absolutely fine. Okay. Follow the steps that they give. Analyze the information in the spectrum to determine the structures of L and M. Just scroll through, bear with me. Okay, right, so you got that big broad peak. Now, if you want to label the graph, what you're going to have to do in your text is you're going to have to say, please see graph. Big absorption there. Remember, you can look at it upside down. It's absolutely fine. I like to encourage people to actually look at it upside down like that. You can actually see the peaks just jump out. You've got that one there, and that one. It's just a bit messy. That's the fingerprint region, really. But evidence of carboxylic acid definitely there. The IR is a very broad one, 1,550. Oh, sorry, mistake. You've got 1,550 to 1,800, and you've got a CO carbonyl, and you have 2,300 through to 3,700. That's your broad one, and the OH in the carboxylic acid. There you go. That's basically your evidence. Now, if you've got a big thumbprint absorption over here, that's a dead giveaway. Carboxylic acid always. The evidence of the alcohol 3,2 to 3,7 linked to the OH in the alcohol. It's a primary alcohol as oxidized, or it's an alcohol as it forms a carboxylic acid. Okay. Identification. So you can then identify it as being the dicarboxylic acid. There you go. It's at either end. Just leave that there for you. Remember, that one will oxidize all the way through because it's a primary alcohol. That's the equation. Just bear with me, I'll flip this out the right way. Okay, sorry about that. There we go. Okay. The monomer will be that, and then you've got the polymer, which then polymerizes to that. Okay. Just hold that there. So, that must be it. Any more to this? End of the question paper, and that's what we like to see. So, I'm going to go off and revise my my organics, just to make sure that I'm a little bit sharper on this particular question, which caught me out a little area earlier. Where it is, there you go. It required an acid catalysis, Phosphoric acid, I'm just thinking back in my mind, phosphoric acid would actually be a good acid to use for this step. I think phosphoric acid is the acid catalysis that allows you to just put a plus on there and then it just springs open. So it came to me eventually. That's why you had to look through your paper. But I remember there was actually a way of remembering. So I actually had the C and the C, and I just thought, you know, famous brand Coca-Cola. And I just thought Coca-Cola, and then you've actually got phosphoric acid inside your Coca-Cola. So that's the reason why I just remembered phosphoric acid as being that acid catalysis. Anyway, all came good in the end. Really, really good luck. Really wish you good luck in your exam. Thank you for watching, and I hope it was useful. Bye for now.